Standard machine learning courses present a pristine digital environment. You write the code, you load a static, perfectly organized dataset, and the model trains. But the physical world does not work like that. It is chaotic, hostile, and constantly shifting. Take the problem of predicting biodegradability. Whether a polymer breaks down in the real world depends on a complex combination of independent variables: its molecular structure, the specific microbes in the environment, the moisture levels, and time. Systemic intelligence relies on a multi-layered, closed-loop architecture designed to interact continuously with these physical variables. The first systemic bottleneck occurs at the ingestion point. This is where the system attempts to capture physical reality and translate it into digital signals. Standard data pipelines assume the inputs will be clean and complete. When applied to the physical sciences, this assumption creates a severe vulnerability. Algorithms alone do not discover scientific breakthroughs. Complete systems do. Any system unable to survive the friction and messiness of raw reality will break down long before the computation phase even begins. This animated diagram illustrates a boundary layer attempting to ingest raw chemical and environmental data. This is the exact moment the system meets reality. Datasets in the real world frequently lack essential values. A spreadsheet might record a polymer structure, but completely omit the temperature or the soil conditions of the test. Even when data is present, scientific literature often provides conflicting labels for the exact same material, making the ground truth highly ambiguous. Faced with these missing contexts and contradictory inputs, the ingestion point chokes. The inconsistency corrupts the initial digital signal. Handling data uncertainty is the mandatory first step. If the ingestion layer fails to account for this noise, every downstream layer in the architecture will confidently learn from garbage. Once the raw data passes the ingestion point, it enters the representation layer. This layer is responsible for converting messy chemistry into structured formats the machine can actually read. This split-screen diagram displays two different methods for structuring data. The bottom half shows a tabular representation, which maps specific chemical features, like the presence of ester bonds or levels of crystallinity, into rigid binary values. The top half shows a graph representation. A graph is a data structure where entities are represented as nodes, and the relationships connecting them are edges. This method maps the complex interactions between polymers, their chemical features, and the specific environments where they were tested. Choosing how to structure this data introduces the second major point of failure: the feature problem. Relying on a single, naive feature to predict behavior creates a weak signal. An ester bond might generally promote degradation, but isolating it ignores the rest of the molecule's physical reality. To capture actual physical behavior, the system must build combinatorial features, linking the ester bond, overall crystallinity, and the specific microbial environment into a single cohesive representation. Representation dictates how the system perceives reality. If you provide a shallow or flawed representation, the system will process it perfectly and output entirely incorrect conclusions with absolute certainty. The structured data now flow into the computation layer. Here, we utilize models like random forests to process the information. A random forest is an algorithm that builds multiple decision trees during training and merges them together to form a more accurate and stable prediction. This diagram shows a decision tree architecture in action. The model applies mathematical weights to the features we just structured, hunting through the pathways for predictive patterns. For a known polymer from the training set, the model quickly finds a stable pathway and outputs a highly confident prediction regarding its biodegradability. This high confidence introduces the overfitting problem. Overfitting occurs when a model memorizes the exact details and noise in its training data, ruining its ability to perform accurately on new, unseen inputs. It learns the specific data points rather than the underlying physics. We can expose this flaw by injecting a completely novel polymer structure into the data flow. The internal logic pathways immediately scramble. Because the model memorized the past instead of understanding the chemistry, its confidence score collapses to 0. Predictive interpolation, simply connecting the dots between known examples, does not constitute intelligence. High accuracy on a training dataset is an illusion of competence. True systemic capability requires friction and resistance from data it has never seen before to prove its actual understanding. To break this false confidence, we implement the evaluation layer. This acts as the system's truth engine. This network diagram illustrates the mechanics of cross-validation. Cross-validation is a statistical method used to evaluate models by intentionally hiding subsets of data during training, forcing the system to prove it can generalize to the unseen information. The model generates its theoretical predictions, and then the physical ground truth collides with those outputs. The system physically trims the incorrect logic branches. Pathways that fail the reality check are dissolved, while the pathways that accurately predict the unseen data are reinforced. Evaluation is the strict mechanism that separates a scientific reasoning system from a statistical guessing machine. It transforms blind pattern matching into reliable, verifiable trust. With a stable, trusted model, the system transitions from predicting knowns to the discovery layer, generating entirely new scientific knowledge. This diagram shows the system extrapolating outward. Using the rules established in the validated graph, it proposes dozens of novel, untested polymer structures. This immediate generative explosion creates the selection problem. Generating new hypotheses is mathematically trivial, and it quickly produces overwhelming noise. Generating infinite permutations is not the same thing as scientific discovery. Left unfiltered, the system simply creates thousands of useless combinations. To solve this, we implement a strict scoring layer designed to evaluate these new hypotheses. This layer applies multivariable filters. It calculates the raw model confidence, checks the underlying feature strength, and verifies the specific evidence supporting the new node within the original graph. The result is aggressive, calculated pruning. The vast majority of the branches disintegrate, leaving only the most viable, mathematically sound hypotheses. A successful discovery system is not measured by the sheer volume of ideas it generates. Its value comes entirely from the ruthless precision of its search and selection process. Even the highest probability hypothesis remains a theory until it faces the ultimate bottleneck: physical laboratory testing. This requires the final, essential mechanism of the architecture, the feedback loop. In this animated diagram, a confirmed physical lab result produces a return signal that travels backward, routing directly into the origin of the computational system. This real-world feedback permanently anchors the new knowledge into the graph. The system immediately adjusts the surrounding weights, updating its internal logic based on hard physical evidence. This zoomed-out diagram reveals the entire macro system operating simultaneously. Raw data flows in, gets structured, runs through the computation and evaluation layers, and cycles through a constant loop of physical feedback. True intelligence requires a continuous, adaptive architecture that turns raw data into structured perception, makes decisions, and evolves through relentless contact with reality.